Our next speaker is Shmuel Oren, and I'll let him tell us the title of his talk.
Okay, thank you for sticking around, and thanks to organizer for giving me the last word. So I'm going to talk today. I'm not going to talk about pricing. This talk is a joint work with Jain Shi, who is my PhD student, and she has done, of course, all the work. I'm doing the talking. And I'm going to talk about how to mobilize, to use computers as a way to achieve more flexibility out of the infrastructure that we currently have. So first of all, why do we need flexibility? This kind of shows rapid penetration of renewables. California is aiming, actually already achieved 33% renewable portfolio standard by 2020. And that consists of wind and solar. And the problem is that wind is very unpredictable. Until you get, this is called the spaghetti chart, until you get very close to real time, you don't know how much you're going to get. Furthermore, it's negatively correlated with load. Most of the wind blows at night when we don't need it. On the solar side, we have what you have seen previously. This is known as the duck curve. And that basically shows by 2020 that during the normal hours, a lot of the supply is going to be produced by the sun, and that creates sharp ramps down and up, and also it creates an overgeneration problem during the middle of the day. So in order to deal with all that, the new challenge to the system operator is that they need flexible resources mix that can react quickly to adjust electricity production, to meet the sharp changes in electricity, and to produce, to react to net demand. So this is we have ramping requirements, we need flexible resources, and we need to mitigate the overgeneration.
Can you go back and explain the duck curve, because I've seen it so many times.
The duck curve.
I don't know what it means.
So the duck curve, this is the original load profile. Now, during the day, you start to produce more and more solar. So what the solar does, it satisfies part of the demand. So this represents what you still need, the net load that needs to be satisfied by the standard portfolio of gas turbines and whatever you have.
So this is load with a minus.
So the load minus the solar is this. So this looks like a duck, right? It looks like a duck, it quacks like a duck, must be a duck. So this is what gives a headache to the system operator, how to deal with those ramps, and how to, to encourage generators to respond. Because generators in the United States have the possibility to either submit economic bid or to submit a physical, say, I want to produce that much during those hours, and they will pay for congestion. So we need somehow to monetize, to give them an incentive to respond to signals and that's why we pay them for those generators that are capable to move fast. We want to encourage them to move fast, or to install governors that is going to enable them to move fast, and that's why we pay for ramping capability. So we create new products that are going to encourage people to incentivize their behavior to respond to the need of the system operator. Now, we can do it on the demand side as well. So these are the challenges, and there are different ways to respond to them. So first of all, you can invest in more flexible generators. Gas turbines can install equipment that will enable them to go up and down very fast. We can make the transmission more flexible, which is what I'm going to talk in here in this talk. We can mobilize demand response. These are all the TLCs, thermostatically controlled load that we can incentivize to respond, and storage, of course. So those are different ways to provide flexibility, and as I said, we are going to focus on that part, which means that the transmission system that traditionally had been considered as a fixed asset, a network with capacity constraint, actually has embedded flexibility that we don't utilize. We don't utilize it because there is no incentive to do that. We also don't utilize because doing that would require a lot of computation that we don't have. But now we do have computation, so we can do that. So we are going to focus on two ways to make the transmission assets more flexible. One is called topology control, which means that we are going now to dispatch the system while at the same time controlling the topology by switching lines in and out of the network on an hourly basis, depending on the optimization. I'll show you why that can help. The other way is flexible line rating. We can take advantage of the fact that the constraint on transmission lines are really mostly thermal constraints that try to prevent the sagging from the line hitting the floor when it gets too warm. But that happens, there is some thermodynamics. A line doesn't hit instantly. So you can actually operate it at a higher line rating if you're only going to do it for a limited amount of time, and then you're going to follow it by a period of cooling off so that it will have a chance to recover. So instead of having a fixed constraint, you can modify the constraint to say you can actually control, you have more than one limit, and you can control that limit when you're going to enforce the tight constraint, when you are going to enforce the loose constraint, and for how long. That, again, makes the problem more complicated mathematically, but we can do it. There are fax devices that I'm not going to talk now because that's new equipment that require a lot of investment. So we are going to focus on just trying to mobilize the existing grid and try to make it work, perform more flexibly. So let me start by topology control. Topology control has been studied for many years. There is a wide literature on that. You can relieve abnormal condition, reduce Eastman losses, reduce operating cost, and the idea is to utilize the assets that you already have without additional costs, just switching lines in and out. That's a relatively simple thing to do. Now, we had a big project on that, but let me first explain why that works. So if you have a 3-node system, this is a system generator A, generator B, and this is the load. And we assume that all the impedances or the susceptance is the same, and we have flow constraint. Now, Kirchhoff law tell you that every megawatt generated here a third of it will go this way, the long way, and 2/3 will go this way. So you can write a set of linear inequality. This is the polyhedron that is going to define the limits on how much you can inject in generator B and how much you can inject in generator A. So now if I want to supply 200 megawatts at location C, this is the optimum point. So this is the optimization. The optimum cost is going to be $20,000 an hour, 100 megawatt generated at A, 30 at B, and 40 at B. However, if I'm going to cut this line out, now this is the polyhedron. So now this is the optimum point. And now this optimum point generates 200 at A, 50 at B, and you reduce the cost to 15. So by cutting a line out, this is almost like the Brecht paradox in transportation. By cutting a line out, we actually reduce the cost of supplying the demand. Now imagine that you have a big network. You can do it selectively, yes?
Why there is the line in the first place?
What? Why is the line there in the first place? For reliability reasons. Because you're trying to, the system, the transmission system is built inherently with a lot of redundancy because of.
For that optimization, you are not considering reliability.
Well, we do it for a short time, but in a large network, we can actually also enforce reliability. And the reliability constraint usually in electricity is n-1, meaning that if any line fails, the system can still sustain, support its load. So we can still satisfy, we can impose that as additional constraint. I'm going to abstract from some of that in the examples, but we have done that. We have, in fact, a paper here, which is, I don't know where it is. Anyway, we have a paper that we do with n-1. So the idea is that you can selectively cut lines out that you don't always, that you build them for redundancy. You know, it's almost like having a four-wheel drive. I mean, you put extra four-wheel drive so that you can climb a high mountain, but you are not going to use all the four-wheel drive when you go on the freeway. That's wasteful. So you disengage the four wheels. That's essentially the same idea. So this is topology control. This is actually done in practice. You know, if you look at the operating manual at PJM, they have a list of lines that can be switched out under different conditions. New England operating procedure 19 specifies disconnecting lines as actions. The problem is that they don't optimize those things in real time. They do it it's a static protocol that you follow. And what we want to do is to do it more actively by using computation. So we actually got a project from ARPA-E in 2012, $5 million, was a joint project, Texas A&M, Berkeley, Arizona State University, and several other institutions to demonstrate the commercial viability of topology control. And we have shown, for example, using data from PJM, that over a period, we took a high load period, and we have shown that over that period, we could have saved $100 million by curtailing one line at a time, just one line, the best line that you can. Yes?
Is there any issue of instability due to transients when you?
Well, we can check stability, and we always do that. But stability usually is checked offline. You don't.
What I meant was instability due to transients. So when you change topology.
During the transient. That's a problem that we have considered. That's possible. But again, when we do that, first we propose lines to take out, then we do simulations like you always do when you take actions to see what it will do to the system, and you do all these online simulations. And that's something that we have considered. So this was a successful project. In fact, there is a consulting company, but Tabor's Associates, who are still, they got a follow-up. They're trying to promote software for doing that at the different ISOs. Now, what we want to do here is different. We want to now demonstrate how we can use topology control in the framework of a two-stage stochastic programming of stochastic unit commitment. We want to use topology control as a recourse action that is going to give us a hedge against different realizations of wind supply. So the idea is that we formulate the problem now as a two-stage stochastic program. Two-stage stochastic program is actually an idealized version of what currently is being done in the market. The different ISO essentially do a market solution, a market implementation of two-stage stochastic programming by having a two-settlement system where you have a day-ahead market and then you have a real-time market. And the people in the day-ahead market submit bids anticipating the uncertainty. And then in the real-time market, when the uncertainty gets reserved, then they have a second bite of the apple, and they can dispatch, adjust the dispatch of their, redispatch their generators. So if you're trying to represent that somehow, a two-stage stochastic programming is a good way to capture that. It's you can think of the current implementation as a crowd solution to a two-stage stochastic programming. So we are going to consider a stochastic programming in which we allow topology control in the second stage as a recourse action against once you realize the uncertainty in the wind forecast and you know exactly what's going to happen. The way the system works currently is that you have a day-ahead determination of which resources are going to be dispatched, and usually it's important for some slow generator that take a long time to warm up. And then the more flexible generators are being dispatched very close to real time. There is a 15-minute market, in fact, and the slow generators are dispatched very close to that in order to provide adjustment capability. So in this framework, we're going, so essentially what we have here is stage one, where you are committing the slow resources. So the decision variables in that here are binary variables primarily, because you decide which generators are going to be turned on and off. Then the renewable, you get a realization of the uncertainty. And then in the second stage, you commit and adjust the output of both the fast and the slow generators in response to how much renewable energy you actually got.
So the transmission that you consider here, I would assume mostly is about turning off a line, not turning on a line.
Well, it depends if the line was turned off in advance. Yeah, it's primarily turn off, line cutting out lines. Yeah. Yes.
What's the benefit of cutting the line off? It changes the price point of that generator.
What?
What's the benefit of cutting a line in your model?
To cut a line, you redirect the flow.
I agree, but
You redirect by redirecting the flow. You move congestion. You can reduce congestion on certain lines and allow other generators to run. So it's a matter of by manipulating the topology, you redirect the flow, and you can affect the redispatch. So generators they couldn't run before because of a constraint. Because remember, every line also forms a constraint. It's like having if you overload the line, it's like having a short circuit at home. So if you cut it, then you eliminate the flow on that line, so you won't have that. So you eliminate that constraint.
if you don't have congestion?
Well, we actually have a theorem that we show that in a multi-period unit commitment, when you optimize over multiple time, even without congestion, you can benefit from changing the topology. And I won't go into that. So this is we have a two-period example and showing if you have one period, no congestion, no benefit from disconnecting. But in a two-period optimization, you can have benefit from changing the topology even without congestion.
Could you give some insight on, more kind of most of the realistic systems in which I would assume the wind farm is somewhat isolated from the main grid? In those kind of a situation, why would cutting off a line be beneficial?
Well, I mean, if you have a radial connection to a wind farm, I mean, obviously you may not. But you know, it gets complicated once you start to have a network. It's very hard to predict. So anyway, I want to move faster. So this is, you know, the formulation of the stochastic unit commitment. You have system market clearing price, clearing constraint, DC power flow, line capacity, constraint, number of lines that can be switched off. So we actually put a limit on the number of lines that can switch off as a way of pruning the tree. Because if we're going to put a binary variable on every transmission line, and that becomes a horrendous combinatorial problem. So one way to control the complexity of the problem is to say, okay, we're going to find the 5 best line to switch, or the 10 best line to switch, and this reduces the complexity. We have generation capacity constraint, ramping up and down, mean up and down, on off. Now again, this is an approximation, DC power flow. in fact, once you find a solution, you have to test it, whether it will be valid in an AC formulation, and sometimes it's not. So there is always a second stage to test the validity of what you're trying to do. But this is what we're trying to do. This is the way you formulate the topology control problem. Basically, you relax. There is a bit theta formulation. Usually, you have the flow is the susceptance times the line, the phase angle difference between the two nodes on an edge. And what we want is we have a binary variable r that says whether the line is in or out. If the line is out, then this becomes 0. The flow becomes 0, but you also have to relax this constraint because you have to allow the angles on the two edges to kind of move independently, and you use the big M formulation to do that. So this is what we do to replace this constraint in the power flow. There is an alternative formulation that uses flow cancellation, where you keep the system intact. You don't cut the line, but instead you find a configuration of transactions that input injection and ejections that if you execute them, it will make the flow on that line 0. And that's an alternative formulation. Finding those configuration is a fairly complicated problem. If you're only going to switch a small number of lines, it may work out. Once you try to switch more than a certain number of lines, then the computational effort becomes, but this is, I just want to make you aware there's an alternative formulation. I won't use that. This is the network that we are trying to test our project on. It's 180 standard IEEE 118 bus system, 186 line, 19 conventional generators, and we have a wind farm that we tried to put at different locations. Where was the location on here? 89 or something? 86? 26. So the wind farm is at node 26 here. I cannot see it. Oh, it's actually, I guess it's here. So that's the test problem. We do some simulation. Now, in order to be able to do, you need to generate scenarios, wind scenarios. And the way we generate, we generate 1,000 wind scenarios by starting with an annual data set from NREL. They have a data set, so for every location, giving us 8,700 wind speed for every hour of the year. And then what we do kind of a bootstrapping where we extract the systematic fluctuation and fit an ARIMA model so that we end up with white noise, and then we replicate that white noise realization by simulating and then reconstructing the scenarios so that we have the same statistical properties but multiple realizations of the wind. So this is the way you generate wind scenarios. And then once you have the wind scenario speed, you can convert it to power by using a static power curve conversion, which converts wind speed to power. So this is now to solve that problem, it has 48,000 binary variables, 80,000 continuous variables. We solve it on a laptop with a MIP gap of 5%. It took us more than 8 hours, so that's not good. So what we had to do is we developed a warm start heuristic, which essentially we get the solution started, and this is the war start is basically done by using a regular stochastic unit commitment without topology control, and then using the topology control for the most loaded hour, and then kind of mixing them and using that as a starting point for all the other hours, and that reduced our computation to less than an hour. for this problem. So we use the Cplex, and the idea is that you can use warm start in the realistic system by looking at the dispatch the day before. So this is the kind of, I want to go quickly through that because I'm running out of time. I actually ran out of time, right? 5 minutes. Okay, so I'm not going to, we actually did the whole thing. This shows the effect of cost. So with constraints on the number of lines that you switch. So this shows that even if you, with 4-line or 3-line switches, you pretty much realize up to, we had like about 15% cost reduction in the dispatch. That's a lot of money in a realistic system. Now, we did the same thing, and I'm going to switch quickly through the reason that when we don't have a constraint, we use an unlimited number of line switches. We didn't achieve the same MIP gap, so kind of the cost went back up. But this with 10 line switching, we got a pretty good, significant reduction in cost. Now, just to go quickly, we were trying to track down where the cost reduction comes from, and it comes from 4 areas. We reduce the production cost by switching generators that are going to be run. We reduce the startup cost by starting generators that are that it costs less to start them than other generator. We're able to reduce the no load cost, which is the jump in cost when, even if you don't have any load, and we reduce the cost of load shedding. And we did kind of a dissection of, where the cost savings is coming for. We did the same thing with a European model of the European system. And let me just jump to that. We have a European model with 1,000 lines, 679 buses, 7 countries, 667 conventional units, and so on. And this is the exam. This is all of Europe. We got a data set, and we solved the problem there. Now, in order to be able to solve it, we have to do some sort of decomposition where we solve the topology control by country, and but we were able to demonstrate also significant cost savings. I'll jump to the last part. This is the decomposition. This is a long talk. The last thing that I want to talk about was a flexible line rating. So the flexible line rating, the idea is that the line constraints are coming from the fact that when the line heats up, it starts to sag, it can hit a tree, so you put a limit on how much you can transfer through a line. Now, but that you have to recognize that this happens, there is some thermodynamics involved there. So if you look at the physics, this is the heat transfer equation that shows the rate of heating of the line, which is a function of the current square times the resistance of the line. And of course, it's also affected by ambient condition and so on. So it means that what's happening is that that the line is actually, I'm trying to jump, that the line is going to heat up slowly. This means that that you can run the line hot with a high current for a limited amount of time, as long as you are going to then reduce it and maybe either leave it at normal constraint or actually reduce the constraint. We kind of took it. So what you're going to end up is that the constraint is going to look like that. You can choose how you're going to move this step, but it means that you can run the line at this temperature and then allow it to run for short periods of time, and then you have to reduce it after that and give it a cooling period, and then you can do that again. So this means that you introduce binary variables saying the line can run it hot, can run cold, or can be cut off completely. And we did that, and basically you do again the formulation, you use it as a recourse action, and you formulate it. And what you achieve by doing that, this is a hedging mechanism against the uncertainty of the wind. So by doing that, then you can be more aggressive or more, dispatch cheaper day-ahead generator. So the benefit accrues, most of the benefit accrues in the day-ahead dispatch, because you know that you have a recourse action that you can rely on in the second stage. So so this is kind of to illustrate how things happen. So this is the normal rating, and so usually this doesn't make any difference. In most cases, the red represents what you do when you do with the flexible rating. This is what you do with normal, without flexible rating, with normal stochastic unit commitment. The place where you save the money is here, because you see, because of this little spike here that penetrates through the normal rating, that would have resulted in you having to dispatch a completely new generator and reroute it completely from the other, and that can start the other generator, which can cost a fortune. So by recognizing that you have that flexibility to run the line hot for a short period of time and relax the constraint for that period, we have saved quite a bit of money. And that's how we achieve that. So I think I'm going to stop here because I'm running out of time. And basically, this is another example where you can just have a little penetration through the constraint for short periods of time, which is enabled by this flexible rating. So the conclusion is that topology control and flexible line rating can both reduce the operating cost. Flexible transmission network control can mitigate the variability of renewables generation, so the cheaper slow generators can be committed in the first stage. Thank you. Yes.
At least from my experience in renewables, they typically they're based on a flexible cost. So they basically say dispatch me at any point as long as it's not below $0 or negative $20. So I agree with you that you could dispatch more thermal or ramping infrastructure, but I think
now, where are we talking about? Most of the places, renewables are kind of a must take. If you look in Europe, for example, I mean, they have feed-in tariffs that...
I guess I'm more talking about, I'm from Texas, so ERCOT. In ERCOT, you basically sell your power. Most wind generators, they put their power in, they say, dispatch me as long as the power doesn't drop below negative $22 or $0.
As long as the price.
The price, yeah.
Yeah, so they have, so in Texas they have negative prices for, yeah, that's a good thing. California also has negative prices, so that's one way to control. But the point here is that, that may be the solution. You see, I haven't talked about the pricing. I've talked about, if you look at it from the system operator point of view, the prices comes after that, how we're going to but this is kind of the welfare maximization. We are dispatching the system. We're trying to look at what can you do optimally if you dispatch the system so as to maximize social welfare. And what we're doing here is that if you are going to treat the transmission system as being flexible, you can achieve a higher level. Now, how you're going to divide the pie and how you're going to price the thing, that's a secondary problem. And I didn't address it here. Yes?
How would you compensate the transmission right owner if you switch off their line quite often?
Well, the ISO is basically controlling the network. They can give them orders. The only problem that line switching is creating, and when we did our RPI project, that's why we kind of backed off from the idea of doing transmission switching for economics, is that it screws up the forward transmission rights market, the FTR market. Because you reroute, you have an FTR market and people buy rights on lines on point to point, and now you change the topology and that can make them lose money. So this has been a problem, from my point of view, is that you shouldn't, you should do the right thing, even if, the market should follow, but not everybody agrees. But that's why here we're focusing on using the line switching in recourse. Now this is something, once you have contingencies, then the ISO basically has full authority. So you can run the lines at emergency ratings for 30 minutes, you can switch lines, you can do whatever action it takes to mitigate contingencies. So we are trying to recognize that here and say, okay, if you are anticipating that, you know that you'll be able to mitigate contingency with those actions, how can you save money in the day ahead stage? And that's what we are doing. Yeah.
Would you think that curtailment of renewables would compete with your solution to the problem?
With what?
Curtailment of renewables could compete with your solution?
If that's this can be another variable. I have another student that works on that, of trying to impose some curtailability of renewables, saying that you can turn, with wind you can turn the pitch of the blades, or with solar you can, I don't know, have cover your solar panels. But yeah, that would be another mechanism. So this is a simplified problem. I mean, if you really want to solve the full problem, you have to have in your all these other actions that I pointed out as ways to achieve flexibility have all to be considered in the portfolio of recourse actions that you can use. Yes.
How to tackle the combinatorial complexity? So
The what?
the combinatorial complexity. So pick 5 lines out of 1,000 lines, like 1,000 to the power of
Right.
5. They are quite tremendous. So how do you tackle the combinatorial complexity?
Well, as I said, at PJM we're kind of aiming. When we did the topology control project, we say at any point you can switch 1 line per day. Which would be the best line to switch? And just this capability saved $100 million in the simulation. So there is always, and from all our experiment, all our tests, we see that typically with 1, 2, or 3 lines, you basically achieve most of the benefit. So, as I said, PJM has a list of 135 lines that can be, they use it primarily for voltage control, for other actions. But, with now, in the old days, they used to build transmission just for reliability. Now, we're building transmission for economics. We're building redundancy in the transmission line using economic criteria, not just reliability. So if you are going to build transmission for economics, you should be able to consider disconnecting lines for economics. And that's what we're doing. Yes?
Have you looked at using this technique for mitigating cascading failure for problems?
Well, no, we're actually looking the other way. We're looking at how to the question is how fast it happens. Yeah, but presumably it can. We haven't done that. What we are looking at, which is Giorgio, is working on how to allocate black start capability throughout the network and restoration strategy, how to restart the system from 0, which effectively it's the reverse problem. Instead of cutting lines, you keep adding lines in order to energize the system when you start from 0 state. And that's another interesting problem, very challenging. The only way we solve that is by, we have good friends at Lawrence Livermore that gives us access to their supercomputer. So a lot of our effort is really on trying to parallelize a lot of things. I mean, in this case, we didn't try to, it wasn't focusing so much on an algorithm, but rather focusing on the capability of what we can achieve with these strategies. But the algorithms, how do we just build algorithms to be able to get some feasible solutions. But the algorithmic part, I think that's where a lot of the effort should go on trying to parallelize a lot of this computation, figuring out ways to use 1,000 cores in order to address those problems. Because, think about your PC 10 years ago. I mean, 10 years from now, you'll have 1,000 cores in your PC. Yes?
Is it actually legal to go above the line limit?
Well, this is something that it's legal as a recourse. If you look at NERC criteria, they allow you to run 30 minutes of emergency rating, which is 30% above the line limit. So again, by considering it as a recourse action, that we can get away with it. But definitely you have to deal with NERC, constraint. But they do allow emergency ratings for mitigation of contingencies. Whether they're willing to consider wind realization as a contingency, that may be a different issue.
Okay, let's
Thank you.
again.